Hi everyone, welcome to today's video. Today we are diving into mixture designs. We will study how different ingredients can interact together to affect the overall quality of any product you are interested in. This topic is relevant for food scientists, for process engineers, for chemical engineers, for chemists, for pharmacists, or for anybody that is interested in working with multiple ingredients and studying their effect on the overall quality and how well those ingredients interact together to affect that overall quality. Let's get started. A mixture experiment is a special form of response surface methodology because the factors are always the component proportions of the mixture, and these factors always work dependently. This means that the effect of one factor on the response depends on the other factor, and you can't treat these factors in isolation. And for us to actually understand how this work, we need to know the two basic or the two fundamental constraints of a mixture experiment. The first constraint is that the values assumed by any of the ingredient proportions must always be equal to or greater than 0. And the next fundamental constraint is that the sum of component proportions must always be equal to 100. Basically, there are two types of mixture designs. We have the mixture lattice and the mixture centroid designs. Let's begin with a mixture lattice design. These designs define points based on components taking on n plus 1 equally spaced proportions from 0 to 1. For pure components and a polynomial of degree m, we often represent it as cure m. The number of experiments is always defined using the equation cure plus m minus 1 factorial divided by m factorial times cure minus 1 factorial. Let's break it down here. Consider yourself formulating a product with three raw materials, with three ingredients, X1, X2, and X3. And at the same time, you want to study the effect of these raw materials on the overall quality. And you are anticipating using a polynomial of degree 3, which is typical of a spatial cubic or cubic models. So in this case, Q will be equal to 3 and M will be equal to 3. The number of experiments you will need to conduct in this design to actually study the effect of these raw materials on the overall quality will be equal to 10 if you substitute for Q and M in this equation. You are going to end up with 10 experiments. What you will still have to figure out is, okay, I need 10 experiments. How do I get the number of levels? The number of levels is always equal to m plus 1. So we know that m equals to 3, such that the number of levels should be equal to 4. From the basic definition of a mixture lattice design, we assign these levels such that they should have equal distances between 0 to 1. Here we've known that we need to conduct 10 experiments, and we know that we need 4 levels. But what exactly are those 4 levels? To get these 4 levels from 0 to 1, these 4 levels must be equally spaced from this 0 to 1. To do this, we have to divide 0 by m, 1 by m, 2 by m, and 3 by m. We are ending at 3 because m is equal to 3. If we had m equal to 4, we are going to continue to 4 divided by m, right? So that the levels we expect to have are 0, 1 over 3, 2 over 3, and 1, which is actually a point here. Let's explain these principles using a case study. And our case study is formulating a food product which have a required energy level, proteins between 12 to 50%, and it must have a high acceptability rate. The next thing you have to do is to check around you which raw materials have properties or nutritional content that when you combine them together, they can actually give a product with these quality specifications. And in our own case, we've identified 3 raw materials: sorghum, soybeans, and fruit powder. And we've already set the limits of substitution of these ingredients, with sorghum at a limit between 50 to 85%, soybeans between 10 and 45%, while fruit powder is between 5 to 40%. This actually makes sense because sorghum will contribute to the base structure and carbohydrate content. Soybeans will contribute to the high protein content that is needed in the formulation and fat, while the fruit powder will contribute to the overall acceptability and the vitamins desired in the product. You can also notice from here how the limits have been substituted. You can see here that the upper limit and the lower limit of the component proportions, they all sum up to 100. If we take the upper limit of component x2 and the lower limit of component x1 and x3, they will sum up to 100. If you do the same for x3, and the lower limit of component x1 and x2, they will all sum up to 100. So this satisfies the 2 basic constraints of our mixture experiments, which says that x must be greater than or equal to 0, and summation x of I must always be equal to 100%. So each time you set your limits, make sure you check and see if they satisfy these 2 conditions. Now we have our design objective, we have our factors, we have set our limits, we have determined the constraints, we have determined if the limits satisfy the basic design constraints, and we've seen that they satisfy the basic design constraints. So the next thing to do is to determine the degree of polynomial, or the indication of the number of levels. If we say we want to study these experiments using a special cubic model, or a cubic model with degree of polynomial 3, meaning m equals to 3, then the number of levels will be equal to m plus 1, which equal to 4. After knowing the number of levels, we need to go ahead and determine how many experiments we actually need to conduct using these 3 factors at 4 levels. So the number of experiments will be equal to 10 experiments. The next thing to do is to know, okay, we have to conduct these experiments at 4 levels. We need 10 experiments. So what are the specific levels? We do the same as we did previously, dividing 0 by m, 1 by m, 2 by m, and then 3 by m, to end up with levels of 0, 1 over 3, 2 over 3, and 3 over 3, which is equal to 1. So we now know the specific round number we need and the number of levels we need to formulate those round numbers. We now have the levels. How can we combine these levels 10 times such that at any given moment, the sum of component proportion should always be equal to 100%, or unity? If we set sorghum at its upper limit, then the 2 other limits will automatically take the lower limit, since the sum of component proportion must always be equal to 1, or 100%. And you can see these levels are actually in our experimental domain. If we decide to go with the lower limit of sorghum and the upper limit of soybeans, then fruit powder will automatically take its lower limit because the sum of component proportion must always be equal to 100% 1. For round 4, if we set sorghum at its lower limit and soybeans at 1 over 3, then we need 2 over 3 to make up 100% 1. And that will go through for the other experiments until we exhaust the 10 experimental points. We have just designed these experiments using pseudo values. And you can actually go into the laboratory and you conduct these experiments using this type of values. These are just codes. It's always recommended converting these values to their actual values, to their actual percentages, or to their actual weights. So to do that, we have to consider the limit of substitution of the factor limit. And here, sorghum, as you've seen, ranges from 50 to 85, soybeans from 10 to 45, while fruit powder is from 5 to 40%. To do this, we have to consider using this equation. L of I here is the lower limit of component x of I. If x of I equals to 1, if I equals to 1, then L of I here will be equal to 50. If x equal to 2, then L of I here will be equal to 10. If x equals to 3, then L of I will be equal to 5. Then L is the sum of all the lower limits. These are the lower limits, 50, 10, and 5. The sum of all the lower limits will then be 65. Then 100 minus L will be equal to 100 minus 65, which equal to 35. So the equation to convert the pseudo values of sorghum to its actual values will be equal to L of I, which is 50, plus 100 minus L, which equals to 35, times X of I, which is actually the pseudo values of sorghum. The equation will then be 50 plus 35 times X of I. Then for soybeans will be equal to 10 plus 35 times X of I. Then for fruit powder, the equation will be 5 plus 35 times X of I. The X of I for X2 are the pseudo values of soybeans, while the X of I for X3, they are the pseudo values of the fruit powder. If you do the calculations correctly, then you're going to have this formulation table. This is actually how you are going to formulate your 10 samples, your 10 experiments using sorghum, soybeans, and fruit powder to formulate the fruit product you want to formulate, and subsequently optimize it using other optimization tools, which you are going to see in our subsequent videos. The first series of values gives the experimental layout in their pseudo form, while the next series of values gives the experimental layout in the actual form. If we choose to have a sample having 100 grams, then 85 grams will be sorghum, 10 grams will be soybeans, and 5 grams will be fruit powder. So what you have to notice here is that 0 in a mixture design in their pseudo form does not mean absolute 0 in their real form. 0 here simply means the lower limit of component x of I, since the factors are always from 0 to 1. If you found this helpful, don't forget to like, subscribe, and share. Part 2 of this video will be targeting mixture-centroid designs and how you can actually use these designs in formulation. So thanks a lot for watching, and see you in our next video.